Okay, good afternoon. Okay, administrative announcement. Next week I'm not having my Thursday office hour, and that's because it's the same time as the annual Regents Lecture, which is a big deal on campus. They, invite some big shot to come give a lecture, and this one is a computer science person talking about how to develop programming environments for parallel processors. So the whole computer science department is going to be there, including me. So if you were planning on seeing me then, we can make an appointment by email for some other time, like, say, Friday morning. Okay, what's this course about? Well, the thing about computer science is it's not a science and it's not about computers. The discipline that's about computers is called electrical engineering. And computer science isn't a science because, for the most part, we don't sort of do experiments to find out what reality is like. We invent things like engineers. So it's a funny name for the field that we're in. And what we need to teach you is not really how to program computers. Programming computers is really, really easy. The world is full of 12-year-old computer programmers, right? Some of whom actually write programs that they sell and make a lot of money on and so on. So it's easy to do as long as the project that you're working on is small enough so that it can all fit in your brain at the same time. When it gets hard is when your project gets big enough so that when you're working on this piece over here, you can't remember what you did in that piece over there. And what we need to teach you, not just here, but over the next 4 years, is how to cope with complexity in projects, in programming projects. And the basic idea is that you invent a system in which you can divide your project into chunks. So you have little chunks made up out of primitive operations that the computer knows how to do, and then you have medium-sized chunks made up out of little chunks, and you have big chunks made out of the medium-sized chunks. And if you do it right, you don't step on your own feet doing something over here that messes up something over there. So the way in which you avoid stepping on your own feet is called a programming paradigm. Basically, it's a set of rules that you follow that I'm going to write the program in this particular style. And there are bunches of them. We're going to look at 4 of them over the course of the semester, 2 at some length and 2 just barely touching on to let you know they exist. So right now we're doing functional programming. We spend the most time on that one not because it's the best or anything, but because, first of all, it's one that you're probably not already familiar with, and it serves as a good basis for understanding the other ones. You'll understand that more as the semester goes on. We spend about a month dealing with object-oriented programming, not more than that because in 61B you're going to do object-oriented programming until you're sick of it. And you've probably seen it before anyway. So our goal in terms of object-oriented programming is not really to make you skilled at it, but rather to try to put you in a position where you can understand it sort of from the outside and see what it is that makes object-oriented programming object-oriented and how it compares with other ways you might approach problems. And the 2 that we're barely touching on, one is client-server architecture. This is, of course, the way things work on the internet, by and large. You have a program running on your computer that talks to a program, at Google or somebody, Yahoo, whatever. And your program is the client, and their program is the server, and they work by cooperating with each other. And finally, declarative programming or logic programming or rule-based programming is a really cool way of writing programs in which you don't tell the computer how to do the job at all. You just sort of ask questions and it you get answers by magic. And we're just barely touching on how it works so that you can pursue it further if you want later. The big idea is abstraction, and there's a picture here of different levels of abstraction. So down at the bottom is how the world works, quantum mechanics, and on top of that is a sort of simplified version of quantum mechanics as applied to a particular problem, namely building electronic circuits, called solid-state physics. And on top of that, we have a physical abstraction called a transistor, which for our purposes in the computer world is basically a remote-controlled switch. And out of transistors, we build circuit elements, which are called logic gates, no relation to Bill. And then out of those things, somebody designs a computer architecture that has a machine language that the computer actually understands. On top of that, we build low-level languages like C. Low is not an insult, by the way. It doesn't mean it's bad. It means that it's less abstract. So when you're programming in C, you think a lot about how the computer actually works, how information is physically represented inside the computer. Whereas in a high-level language, we try to protect you from having to worry about how computers work, so you can be thinking more in terms of the problem you're trying to solve, which is the application program up at the top of the abstraction hierarchy. Java, which you'll use in 61B, is sort of an in-between level language. And you'll see some things about that later in the semester too. In our program, our educational program, not computer program, we start at the top and work our way down, the abstraction hierarchy. Some schools do it the other way. Well, not at the very bottom, but they'll start at the level of computer architecture and build up to higher levels of abstraction, on the theory that if you really know how everything works, you'll understand better the steps further up. You'll feel more confident that what you're learning can really happen. We do it top down on the theory that we want you to start out thinking in the language, not the programming language, the sort of English language, that we expect most of you will spend most of your working careers in. So this is sort of where you want to be grounded, is at the higher level of abstraction, and then later on we peel away some of the layers of abstraction so you can see how it actually does work. And if you want to get below here, you take EE classes and then physics classes. And then I guess philosophy classes or something. Okay. Yeah, I think that's all about the structure of the course, because we're running late. So I have a program here called Argue, up on the screen. Let me show you how it works. I say argue of, I like spinach. It says I hate spinach. And so on. So what's the structure of this program? Well, you can see argue up at the top of the screen. Its argument is the sentence S. If S is the empty sentence, then we return the empty sentence. Otherwise, we split the sentence up into its first word and all the rest of the words. We have a helper procedure named opposite, which we call with one word, the first word of the sentence, as its argument. And then for the rest of the words, we call argue recursively. And we take those results and combine them together with the call to sentence. So this is the paradigmatic example of a recursive function. Well, a paradigmatic example. Supposedly you all know about recursive functions. That's the prerequisite. So I'm not going to spend a lot of time on this in lecture, but let me just spend 2 minutes trying to convince you that when you see that call right here, argue of but first of S, do not think go back to the top and do it again for the rest of the sentence. If you think like that, you're doomed. Because you're not just going back and doing it for the rest of the sentence. You're calling argue on the rest of the sentence, and then there's still some work to do, namely that call to sentence right here, which if you think go back, you're going to forget to do. So the way you have to think about it is we do the recursive call on a smaller case. We get a result from that, and then we're still in the same call for the entire sentence, and we stick the result of opposite of first of S in front of the result from the recursive call. So the way to think about this, if you get confused, is the following. Even though I said we're going to look inside the computer much later, I'm going to peel apart all these levels and tell you how computers work. Inside the computer, there are a whole bunch of little people. And each person in the computer is a specialist in running some procedure, some function. So there are sentence little people, and there are opposite little people, and there are empty little people, and there are argue little people. So when I ask one particular little person to do argue of I like spinach, that person, let's call her Amelia, goes out and hires another different argue person, like Alonzo, let's say, to do argue of like spinach. And then Alonzo finishes his job and says, hate spinach. And then Amelia sticks opposite of I, which turns out to be I, in front of that, and that's how we get the result. So that's how computers work. And the reason recursion works is that each recursive call is a different little person, and they all remember, each one remembers individually, I'm doing this task, and here's how far along I am in doing it. Okay, so that's it about recursion. If you still have any questions, see me in office hours or something. So just a moment to talk about how opposite works. Here it is. It takes a word, W, as its argument, and there are a bunch of special case checks. So since we have more than two possibilities, I'm using cond. As you should have seen by now in the reading, cond and if are two alternative notations for decision making. If this is true, do this. If that's true, do that. If is used when there are exactly two choices, true or false. Cond is used when there are a lot of possibilities, as in this case. So if the word is like, then return the word hate. If the word is hate, return the word like, etc., etc., etc. And then at the very bottom, else, if it isn't any of those words, in other words, return the word itself. So that's why opposite of I is I, opposite of spinach is spinach. It's because of that else clause at the bottom. Okay. I'm talking really fast because we have a lot to get through. So I hope this all works. Cond and if, and also define, which we saw last time, are examples of something called a special form. And what that means, let me run over to the other end of the world here. I told you last time that when you see some things in parentheses as a scheme expression, what that means is this one's a function, the rest of them are arguments, and the way scheme evaluates this expression, figures out what the value should be, is step one, evaluate all the pieces. So in order to evaluate the whole thing, we have to evaluate the pieces. That's an example of recursion. And when we get around to looking at a scheme interpreter, you'll see there's a procedure called eval that indeed calls itself recursively for each of these elements of the whole expression. So now we've turned the actual argument expressions into actual argument values. And at that point, we call the function, giving it the actual argument values to work with. So the function never knows what you typed to get those values. Right? If you say plus times 2, 3, 9, or you say plus 6, 9, the plus function doesn't know which one you typed. It only knows the value, not the expression. So that's how Scheme does function calls, except for the exceptions. And the exceptions are called special forms. The word form means expression. It's an archaic piece of terminology. You never see form by itself anymore, really. Well, you do if you're doing CS theory sometimes, but you don't in applied programming classes. You do see form only in the context of special form. So a special form is a special kind of expression, one that does not follow this rule about first evaluate the subexpressions, etc. Why do we need special forms? Well, remember the other day I said define pi 3.14, etc. Okay? Suppose this expression were an ordinary expression. Well, the first thing we would do is try to evaluate all the subexpressions. So the value of define would presumably be the define procedure. That's okay. 3.14159 blah is a number which is self-evaluating. It's its own value. No problem about that. But now we have to evaluate pi. But we haven't defined pi yet. So we would get an error message. Unbound variable, pi. So define has a special rule. And define's rule is it does evaluate this thing. So if I have some expression like, plus 2, 3 here, and I say define v, be plus 2, 3, the value of v is not plus 2, 3. The value of v is 5. Because this gets evaluated, and then this does not get evaluated, the variable name, and it's this variable that gets the value of whatever this expression is. Okay? So this define expression is special. It doesn't follow the usual rules. There are a dozen, 20, something like that, special forms in Scheme. Not very many, in other words, compared to hundreds of primitive procedures that do follow the ordinary evaluation rule. Another piece of loose terminology, almost all the time, people say, you will hear me say, define is a special form. That's not really technically right. Define pi 3.1.4, that's a special form. What define, just the word define is called a keyword. So define is the keyword that introduces a defined special form that has this whole thing. Okay? But everybody says define is a special form, and you just know what that means. So far, the only special forms we know are define and if and cond. Cond, by the way, is an exception in another way, namely, whoops, that's not what I wanted to do. The way it uses parentheses. So the set of parentheses, starting with the open parenthesis where the cursor is blinking, do not mean call this procedure with this argument. They are just a grouping piece of fluff that combine the test expression with the action expression. If this test is true, here's what to do. As opposed to this parenthesis right here, before the equal, which is a regular old Scheme parenthesis that introduces a regular old Scheme expression that's a procedure call. So equal question mark is a procedure, and we're calling it with the arguments of whatever W is and the word wonderful. Right? So please don't think the notation of cond is that you always have two parentheses in each cond clause. I don't want you to think like that, because those two parentheses are very, very different from each other. And in fact, it's not even true, as you can see down here, where there aren't two parentheses. Okay? The way to think is each cond clause is surrounded by parentheses, and what's inside the parentheses is two plain old scheme expressions that can be any expression at all. And if they happen to have parentheses in them, then you'll see two parentheses in a row. Okay? Good. Oops. What have I done? Oh, that's what I've done. Okay, so who speaks Pig Latin? Who doesn't speak Pig Latin? Wow, all right. What did you use when you were a kid and you didn't want your parents to know what you were saying? What? Text messages. Okay. Pig Latin is this little kid language that is supposed to be a secret, except of course the parents know it too because they were kids once. And the way it works is to translate a word into Pig Latin, you take all the consonants at the front of the word until you come into a vowel, and you move those consonants to the end, and then you add AY. So Pig Latin of the word scheme, the initial consonants are SCH. So we push those after the EME. So I have the EME, and then the SCH, and then we add AY, Eamske. If the word starts with a vowel, oops, too many parentheses, sorry. Then it's just aardvark gay, because nothing has to move around to the back. How does the procedure work? Well, if the first letter is a vowel, that's what this helper procedure decides. If the first letter is a vowel, then all I have to do is take my word and stick AY at the end, like the aardvark case. If the first letter is a consonant, then I divide it into its first and its butt first. I take the first letter, just one letter, move it around to the back. That's what this call to word does. Combine butt first of the word and first of the word. And then call piggle recursively on that. So in a case like scheme, there are going to be a total of 4 calls to piggle. One for scheme, one for CHEMES, one for HEMESC, one for EMESCH, and that's the one that finally comes up with a value. Okay? Yeah?
What if you type in the word like fly, F-L-Y?
Yeah, if you type in FLY, this program won't do very well because its vowel question mark procedure is a little simplistic. So for asking that question, you can have an extra homework assignment of writing a really good vowel question mark. Because you don't just want to put Y on the list, because sometimes Y is a consonant. Anyway, you can work on that. But really the reason I wanted to show you this is that I can write this procedure. So I'm going to take a sentence and translate it to Pig Latin this way. Oh, I'm in text mode for some reason. Thank you. Otherwise, sentence, that's the sentence procedure abbreviated. Piggle of first of cent and Piggle cent of but first of cent. Orphe, one, unway, unne. Yeah. So why am I showing you this trivial little example? Because I'd like you to compare the procedure Piggle cent right here in the bottom screen with the procedure argue on the top half of the screen. Both of them have the form shown here. Define something or other of a sentence. If the sentence is empty, return the empty sentence. Otherwise, combine into a sentence some function of first of cent with recursive call to this same thing of but first of cent. This is a programming pattern that by the end of next week, for sure, you will be able to type in your sleep without looking at the keyboard. Because it really comes up over and over and over again. And we'll see actually next week that since it comes up over and over and over again, we have a clever way of not making you have to type it each time. That's next week's big idea. Not every recursion is of this recursive call of the but first sort. So the canonical example that's in my notes here is define Pascal row column on equal column 0, 1 equal column row 1 else plus Pascal row minus 1, column minus 1, Pascal, row minus 1, column. So you know Pascal's triangle? Yeah. It's this thing. In which each number is the sum of the two numbers above it, except that the ones at the ends of the row are 1. You should have met this in high school as the coefficients of a plus b to the n. And it also comes up in probability, a number of combinations of n things are at a time. So the rows and columns are numbered from 0 in this program. So if I want to get this 10 that's circled here, I'll ask for Pascal row 5, element 0, 1, 2, 3. And there's my 10. Okay? The procedure, the reason I'm showing you this again, is that there are 2 recursive calls each time. In that pattern over on the third board, there's only 1 recursive call per call. So it's sort of just a sequence of calls. But in Pascal, each time you call Pascal, you get 2 recursive calls. And each of those makes 2 recursive calls. And each of those makes 2 recursive calls. So if you think about this in terms of go back, you're really going to get a headache. Right? You have to think about it in terms of all those little people with names starting with P inside the computer. Okay. The last thing we're going to do is revisit that business of how a scheme evaluates procedure calls. And I wish this board worked. But when I lift it up, it comes back down again. Someday they'll fix it. That's not fair. They've been trying to fix it for a while now. So, step one. Evaluate the actual argument expressions. Step two, call the function with actual argument values. There's a name for this. It's called applicative order. And there's another possible way to do things, which is called normal order. In which there's really only one step, which is call the function with actual argument expression. So we actually pass the expression down to the procedure that we're calling. And the only exception to that is, that's 1a, and here's 1b. If it's a primitive function, evaluate the args first. So when we finally call something like plus, that's when we finally evaluate argument expressions. So what I'd like to do for the next quarter of an hour is investigate the question, does it make a difference which way you do things? So for the purpose of that investigation, we have implemented two little scheme interpreters. And this is sort of a preview of coming attractions, because writing interpreters for programming languages, which really seems like quite a complicated task when you haven't done it yet, turns out to be not very hard, especially if the language is scheme. So it's no big deal for me to throw together two little scheme interpreters, one that uses applicative order, one that uses normal order. So let me load order. By the way, I told you last time that everything I say is in the course reader. My lecture notes are in the course reader. But the other thing that I should tell you is that all the program examples that I'm typing in here are online. And the file names are in the lecture notes. So don't try to write down the programs because you can just examine them online at your leisure. Okay. So the way this works is, instead of using define to define procedures in this little toy scheme system, I use def. So I'm going to do the example right out of the lecture notes to make sure nothing goes wrong. So f of a and b is the sum of g of a and b. And what's g? Well, g of x is times 3x. Okay. So now we're going to evaluate a call to f in applicative order, which I do this way. I say applic f of, I broke my glasses, plus 2, 3, and minus 15, 6. So, what's special about these little scheme interpreters is that they don't just tell you the answer, they show you some of the steps they're taking along the way as they go. So in this case, here's the call that I made. So in applicative order, step 1, evaluate the actual argument expressions. So I'm going to start by evaluating plus 2, 3, which gives me the answer 5. I'm going to evaluate the actual argument expression minus 15, 6. That gives me the value 9. Then I call f with those values, 5 and 9. Now, how do you call a procedure? Well, if it's a defined procedure, not a primitive, it has a body, which is a scheme expression, right? It has the formal parameters, the names for the arguments, and it has the body. So what we do, and this is true both in applicative order and in normal order, is that we take our arguments, for applicative order, the argument values, for normal order, the argument expressions, and we substitute those for each occurrence of a formal parameter in the body. So if you look at the body of f, let me back up so you can do that. The body of f is plus g of a, b. So I'm going to substitute 5 for a and 9 for b in that body. That gives me this expression, plus g of 5, 9. So now I have to evaluate g of 5 before I can do the plus. 5 is a number, it's self-evaluating, so there's no big deal about evaluating it. So we just go ahead and substitute 5 for x in the body of g. The body of g up near the top of the screen is times 3x. So I get times 3, 5, and that's 15. So g of 5 is 15. And now I come back to this expression here, plus g of 5, 9. I plug in 15 for g of 5. I get plus 15, 9, and that's 24. Okay? So that's how we do it in applicative order. So now we're going to do the same thing in normal order. And this time, here's the expression. Now, without evaluating anything, I take the argument expressions, the plus 2, 3, and the minus 15, 6. I substitute those for a and b in the body of f. And that gives me, the body is plus g of a, b. So g of a becomes g of plus 2, 3. b becomes minus 15, 6. And this expression where the cursor is blinking is something that was never constructed in the applicative order version. So now, in order to evaluate this substituted body, the thing I'm trying to do, the plus, is a primitive. Since it's a primitive, I have to evaluate the argument expressions, the same as I would have in applicative order. So I have to evaluate g of plus 2, 3. But g is not a primitive. So I don't do plus 2, 3 yet. I just substitute plus 2, 3 for x in the expression times 3x. So that gets me here, times 3 plus 2, 3. Since times is a primitive, I now have to evaluate its arguments, one of which is plus 2, 3. Plus 2, 3 gives me 5, so I have times 3, 5, that's 15. Meanwhile, back up here, the second argument is minus 15, 6. Since plus is a primitive, I go ahead and evaluate that. I get 9. I do plus 15, 9, and I get 24. The same answer I got before. So now the question is that always going to be true? Even though we do different operations in different orders, we always come up with the same answer. Somebody yell that no. You all think no? Let's take a vote. Who thinks no? Who thinks yes? Okay. Well, the answer is a little tricky. Namely, the answer is yes if we're doing functional programming. Okay, so here's where our talk about programming paradigms really starts making itself felt. What does functional programming mean? We've been doing it, but I haven't really defined it. A function is a procedure with the property that every time you call it with the same arguments, you get the same value. Okay? So plus, for example, is a function. Every time you call plus 2, 3, it's always 5, no matter what. Whether it's raining or you've done plus 2, 3 before, doesn't matter. Okay? If that's true, and if the expression that you typed is a correct expression, there aren't any domain errors where you're trying to apply a function to an argument that it doesn't accept, like dividing by 0, then the answer is yes. The handful of people who voted yes were right in functional programming. Normal order and applicative order, they do things differently. One might be more efficient than the other, but they come up with the same answer in the end. This is part of an important property of functional programming, which is one of the reasons people find it useful. And I'd like you to really try and sear this into your memory. If you're doing functional programming, it really doesn't matter what order things happen in. That's important for several reasons. One reason it's important is trying to do formal reasoning about computer programs. For instance, you'd like to prove whether your program is going to get the right answer or not. There's been a lot of work on that. It can't really be done in complete generality, but you can do important special cases that are very useful. And in reasoning about a functional program, it's much, much easier because you don't have to worry about the sequence of events. You only have to worry about whether the functions have the right sort of input-output behavior. Another reason this avoiding dependence on ordering matters is, as I'm sure you know, these days it's very hard to buy a computer that isn't multi-processor. So your cheap little PC that you get these days has a dual-core processor, meaning inside that chip there's basically 2 computers. And in order to take advantage of that effectively, you have to be able to take the problem you're trying to solve and have one computer do this part of it and the other computer do that part of it at the same time. So for instance, let's say I'm calling a function with 2 arguments, and each of them has a complicated expression to evaluate. I can say, okay, processor A, do this argument, processor B, do that argument, and then that can be happening in parallel, and then when they finish, we can actually call the function. Well, that only works if it doesn't matter about the order in which those 2 arguments are evaluated. Okay? So if you're doing functional programming, then it's very, very easy to parallelize. That's a point we're going to be coming back to in detail. Right now I've said it in a hand-wavy way, but we're going to see later in the semester, when we talk about concurrency, why that's the case, why functional programs are much, much easier to parallelize. So, normal order, applicative order, same answer if we're doing functional programming. So now here's an example that isn't functional. There's a primitive procedure in scheme called random. And here's how it works. I say random 10. And I'm going to get a non-negative integer less than the argument. So in this case, something in the range 0 to 9. So 10 possible values. Well, is random a function? No, because a function is a procedure with the property that every time you call it with the same arguments, you get the same answer. And that's clearly not true for random. And here's how that plays out for us. I'm going to define in my normal and applicative order toy evaluator a function called 0. 0 of x is minus xx. So you can see why it's called 0, right? Because whatever the argument x is, x minus x should always be 0. So in applicative order, let's say 0 of random 10. Well, 0 of random 10. In applicative order, the first step is evaluate the actual argument expressions. So I'm going to evaluate random 10. It's primitive, so there's sort of innards to look at here. And we happen to get the answer 9. So now I call 0 with the argument value 9. We substitute 9 for x at minus 9, 9, and we got 0 as expected. Now let's do 0 of random 10 in normal order. Here we don't evaluate the argument expression. We take the expression itself and send that into the procedure 0. So we substitute the expression random 10 for x in minus xx. We get minus random 10, random 10. This time, we called random 10 twice. And because of the nature of random, we got two different answers. We happened to get 9 the first time and 3 the second time. So we substitute those values into minus xx. We get 9 minus 3, which is 6, and not 0 at all. Okay? So this is your first illustration of the fact that if you're doing functional programming, sequence of events, the order of a computation doesn't matter. If you're not doing functional programming, then the sequence of events does matter, and things that look completely simple and nothing can go wrong, like this 0 function up here, minus xx, how could that go wrong, do go wrong in normal order. Yeah? In normal order, what if the operation, you mean the instead of random, I had said something that, instead of minus, I did something that was not a primitive. In that case, the two different random 10 expressions would have been passed on to that non-primitive, and sooner or later it's going to call a primitive and use those two things. Okay? And you know, what answer you get depends on exactly what procedure you write. But it will still turn out to make a difference that we're doing normal order instead of applicative order. Okay? Other questions? Yes?
Would there be a way to get rid of the two randoms if you first define another variable after random 10 and then did the minus?
Yeah, his question is, this is somebody who used to program in BASIC or C or Java or one of those. And he says, what if I say, define foo random 10, and then say 0 of foo? And yes, in this particular example, you would get 0. But now you're depending on the order of evaluation. In order for your program to work, it has to be the case that that define foo random 10 happens before the call to 0. Right? And that's the sort of thing that makes your programs harder to debug. Right? Because now we have this variable foo that has a value that we're expecting to use later on. Meanwhile, some other part of the program also used foo for some other purpose, clobbers it, and we're in trouble. So that's how you get in trouble. And that's sort of, this part of the program clobbered that part of the program's data. Can't happen if you're doing functional programming. One more, we have 1 minute. Let me emphasize the point of this whole demonstration is not to convince you that functional programming is the only right way to program. you will meet, you probably have already met, object-oriented programming bigots who say object-oriented programming is the only way to program. But there aren't really too many functional programming bigots like that. Functional programming is a very good way to solve a wide range of problems. Okay, see you next week. The stuff you didn't get in that other school. It's a self-paced class. So you go to the self-paced center and they hand you a worksheet and you do the problem and you turn it in for grading and then you do the next one and so on. And again, in the self-paced center, there's always a huge staff of people to answer your questions and give you feedback on your work. It's okay. Some students who come in with 61B credit tell us later that they were fine about the ideas, but they never really got enough programming practice compared to students who take the regular 61B. So that's just a piece of feedback about it. Okay, it's 3 o'clock, so let's continue this Monday.